Uh, okay, so welcome to the fourth week of this NPTEL course on parameterized algorithms. And as usual, in this week, we will look at the assignment questions that were uh, given in the last offering of this course in 2023. So today's discussion is about some randomized techniques uh, used in the uh, design of parameterized algorithms. So how much charge do I have? Okay, so I think I should put on the adapter. So let's go to the questions. Okay, so this is week 4, and we'll start with the first question, and I'll let you read the question. There are 6 questions overall, so hopefully the next 45 minutes we'll do three questions, and then we will pause, and then we will do the next three. Uh, I mean, as permitted by time. So the first question says that, okay, so what is a leaf? A leaf is a vertex with degree 1. So a leaf is not an isolated vertex, it's a vertex with degree 1. And then there are 5 statements. We have to decide which are true, which are false.
Yes, so in the first, it is in any forest, the number of vertices which are not leaves is smaller than the number of the leaves. So yeah, so yeah, so in a forest there would be many distinct trees, and so in the trees, so how many internal nodes are there? So if there are n number of the leaves, then I guess there would be n plus one number of the internal nodes. So,
Okay.
so if that is the case, then the first statement I think will not be true. Yeah, yeah.
So I will copy this 5 options and I will paste it there on the whiteboard. Let's put the text box.
No, I said reverse. The number of the leaves is equal to number of internal nodes plus one. So the number of the leaves would be higher than the number of the internal nodes. So in that case, the choice number one could be correct. That the number of vertices which are not leaves is smaller than the number of the leaves. Yeah, then this seems true.
Okay. So we have a forest. Let us say this is an example of a forest, and let us also numbers these things. So this is A, this is B, and this is C. So B and C are leaves because they have degree 1, and A is not a leaf. This is internal. Okay. So the statement is the number of vertices which are not leaves is smaller than the number of leaves. Okay. So
Yes,
what are you going for? You're going for true or false?
true, true. This seems true to me because the number of the leaves is equal to the number of internal nodes plus one. So number of leaves would be higher than the number of the internal nodes. Like in this case also, number of leaves is equal to 2 and the number of nodes, internal nodes is equal to 1.
Okay. Okay. Fine. So yeah, in this case there are 2 leaves. I don't know why there is a lag in the handwriting. I think my iPad has become older. The number of internal nodes is only 2. One. So there are more leaves than internal nodes, but the statement is that the number of vertices which are non-leaves is smaller than the number of leaves. So it looks true. But what is a forest? Forest is just uh, an acyclic graph, so that there are no cycles. So how about uh, this graph? Is this a forest?
Yes, and it's a forest, and probably the conclusion which I told you is valid for the binary trees only, and that too for the strict binary tree, I guess, wherein every node has got exact uh, two
Yes.
children.
That is called complete binary tree.
Yes, yes. Yeah. So this is a tree and no issues. Uh, so therefore, the number of internal nodes here is greater than the number of leaves available. Certainly, this is the case.
All right. So this is an example where there are more internal nodes than leaves, but the statement is saying the reverse, that the number of internal nodes is smaller than the number of leaves. So that is not correct. So let's mark it false. Okay, this is fine. Let's move to the next statement. This is done. Let's move to the second one. So in
Yeah. So
any
second, yeah, uh, second one is exact reverse of the first one. So
yes, okay. So what about this?
this has to be true then. Number of vertices which are not leaves is greater than the number of the leaves. But this is not, I mean, not always true. So there could be the cases like in the case of the strict or the complete binary tree. Quite possible that the number of the internal nodes is less than the number of the leaves.
Yes. So that is the case. In this figure on my left is a complete binary tree, and there are two leaves, but only one internal node.
Yes,
So it is not necessary that there are more internal nodes than the leaves. So it is also false. But you are right,
yes,
these two statements are reverse of each other, but these two statements are not complementary in nature. So both can be false simultaneously.
yes.
Oh,
Third option is in any forest with no degree two vertices, in any forest with no degree two vertices and no isolated vertices, the number of non-leaves vertices is smaller than the number of the leaves. So this time we do not have uh, vertices of the degree 2. So if we do not have a vertex of the degree 2 and no isolated vertex, it shows that the forest, I mean the tree cannot be a binary tree. Binary
yes,
tree is, yeah, because in the binary tree the degree of a vertex would be 3 rather, not 2. So what is the meaning of the degree of the vertices of the degree of the vertex is 2. So that is the second case in your figure, the tree of this form, wherein we have a straight line kind of the thing. And neither we have, so we cannot have a straight line. For the binary, we can have a vertices with the degree 2, I guess, not 2, but would be 3. Yes, so this refers to the second figure in your diagram, and neither we have an isolated vertex. So the number of the non-leaf vertices is smaller than the number of the leaves. So if we do not allow this straight line kind of the thing, then we will be having a tree-like structure, a binary tree-like structure. So then this statement will become true, that there would be less number of the internal nodes than the number of leaves available. But this says that the number of non-leaves vertices is smaller. So this seems to be true then. Yeah.
Hmm. So, yeah, your reasoning is more or less correct only. I will repeat it. So there is no degree two vertices. So degree two vertices are not allowed, but degree one vertices and degree three vertices are allowed. Isolated vertices are also not allowed. So that is all the restriction on the forest. So such a thing is allowed. That okay, degree one, and then be after that degree three is allowed. After that, this can become a full binary tree kind of thing. Uh, yeah. So this is a figure. So every vertex has degree one or three. This is allowed. Okay. So the number of non-leaf vertices is small. So in this figure, we can see that there are how many leaves? Five leaves. 2 plus 2 plus 1. Whereas there are only three non-leaves. So there are less non-leaves than leaves. So this looks true. So the only difference with the complete binary tree is that you do not want the root to have another subtree. If there is a root, the root has only one subtree, and that is a complete binary tree. Okay, so a more formal way of proving this will be the following. That suppose that the number of leaves, let that the number of leaves be P in the forest. No, P, let's say L for leaves, and the number of non-leaves be P. Then what can you say about the number of edges in this uh, forest? Non-leaves. So how many edges?
So yeah. So if the number of leaves be L and the number of non-leaves be P, so leaves definitely would be contributing. Each leaf would be having degree one. So then L plus, and then because we can take the help of the fact that the sum of the degrees of the vertices is equal to the twice of the number of the edges. And will this work for the trees as well? Or no, number of edges is equal to n minus 1, number of vertices minus 1. And so
Yes.
L plus P minus 1 is equal to the number of the edges.
Yes. So you are right. Because this is a tree. In a tree, the number of edges is one less than the total number of vertices. But a forest could be a union of multiple trees. In that case, the number of edges can be even smaller. So we will say that number of edges is at most L plus P minus 1. Because if there is another tree, the two trees can form a forest. And let's say one tree has five vertices, the other tree has another five vertices. So overall 10 vertices. But the number of edges is 4 plus 4, 8 only. So two less than the number of vertices instead of being one less. So L plus P minus 1, that is one less than the number of vertices, is an upper bound only on the number of edges. All right. Hello.
Yes, audible.
Yes. So I'm saying that if there are two trees in a forest. So a forest could be tree one and tree two. Union of these two things together can be a forest. Now, what you have said that inside a tree, inside one tree, one connected acyclic graph, the number of edges is exactly one less than the number of vertices. That is true. But if you have two trees together which are disconnected, so there is one tree which is a connected component, another tree which is a connected component, but between the two trees there is no connections. Then the number of edges could be even smaller because if there are
Yes.
five edges, yes. So yeah, so yes, fine. So therefore, now we will do the sum of degrees argument. So if the number of edges is this much, then what is the upper bound on the sum of degrees?
Twice of, so
Yes.
twice of the number of the edges.
Yes. So now what do we know? We know that this graph does not contain anything but this. Uh, so this is a forest which does not contain any degree two vertices, and so all the other, did it say that degree? Uh, so what degrees are allowed? Degree two is not allowed, and degree zero is not allowed. So one is allowed, three is allowed. But what about larger degrees?
So I think that since the degree one is not allowed, so it means that we can have a situation wherein the number of internal loads is greater than the number of the leaves. I think this is the only situation wherein the number of internal loads is greater than the number of the leaves, wherein the vertices of the degree one are allowed.
Yes. So, but I want to say something about the total number of degrees in terms of the sum of degrees in terms of the number of vertices. So sum of degrees can be written as, so all the leaves will contribute exactly one to the sum of degrees. So we can say L plus the rest of the vertices will contribute. Let us say the 3 degree vertices will contribute some three into, let us say there are P3 3 degree vertices, P4 4 degree vertices, and so on. But overall, the sum of degrees is going to be at most 2 times L plus P minus 1. All right. So by I denote the number of vertices with degree I. This is notation. So we have just written sum of degrees like this. Now, can I write these other terms? So I can replace 4 by 3. So that will be a smaller number. So I can say that L plus for every vertex which has degree 3 or more, I am counting only degree 3. So we know that the rest of the vertices are at most exactly P. The number of non-leaves is P. That is what we assume. So that is at most. Now I am expanding it. Now we can do this simplification. So this small l goes to the other side and this 2p comes to this side. So p is at most l minus 1, or in other words, l is greater than p plus 1. And if it is greater than p plus 1, it's also greater than p. So therefore, the number of leaves is at least the number of non-leaves. So that is what we wanted to prove. So are
And
these
yeah,
steps? Yeah.
yes. So in this, I mean, while simplifying this expression, We
Oh,
wrote 2L plus 2P minus 2, I think. Yeah.
sorry. But it does not matter as far as the counting is concerned. The comparison will still work because if L
Yes.
is greater than P plus 2, it is also greater than P. But thanks
Yes.
for pointing out the error. So that is a formal way of proving that with a tree where there is degree one vertices, degree three vertices, degree four vertices are also allowed. But if that is the case, then there are definitely more leaves than non-leaves. Fine.
Yes.
So let's go back. Okay, so third one is done. Now this is video specific question. Uh, so if you have watched the video, you can read it. Otherwise, we'll discuss it. So we discussed randomized fixed parameter tractable algorithm for the feedback vertex set. So used some pre-processing rules so that in the case of an AS instance, if we have a feedback vertex set, then the fraction of edges going out of G minus S. That means once you have removed the feedback vertex set, you know that all the cycles are killed. So G minus S has become an acyclic graph. So the fraction of edges going out of this acyclic graph compared to the edges which are internal to this acyclic graph uh, is at least 50%. So that is the statement. So I'll give you some context. Let me give you some context. So I'll first copy this statement. I'll just take it back on the questions. So these two questions. Okay, so the last two options are opposite of each other. So either it is 50% or it is less than 50%. Means either it is more than 50% or it is less than 50%. So I will copy these two options. Uh, Once again, let's take the text box. So what has happened really in this randomized fixed parameter tractable algorithm? So you are given a graph and you are given a number k, and the question is, as usual, can you delete? Can you delete k vertices such that all the cycles are removed? So there is a feedback vertex set. So does there exist a feedback vertex set of size at most k? So uh, so the algorithm has two steps. So in the first step, some pre-processing rules are applied. So what happens is in the pre-processing rules, means some reduction rules, you get from g comma k to a graph g dash comma k dash. Okay. So the rules are not too important, but let me see if I can write it quickly. Yeah, I think this I discussed some. So in the context of feedback vertex set, we have discussed it already. So we can maybe quickly recall what are the rules. So the reductions rules are the following. The first reduction rule is that it's RR1. Yes. So if there is a self loop, if there is a vertex in the graph V which has a self loop, so you must delete this vertex because if you do not delete this vertex, then how will you kill this cycle? So in order to destroy this cycle, you must delete this vertex with a self loop. So the rule is if you have identified a vertex with a self loop, then you delete it. So you and then you ask that okay, after deletion of this vertex, so in G minus V, can we still delete at most k minus one vertices so that the graph becomes acyclic. K minus 1 because one vertex V is already deleted. So your budget is decreased by 1. Okay. Is it clear?
Yes, yes.
Okay. And then second rule is sort of like this. So if there is a cycle like this, so between U and V, you identify that there are parallel edges. In fact, you identify that there are multiple parallel edges, more than two, lots of parallel edges. Then you say that, okay, I need not worry about so many loops. I should worry about only one loop. So I can rather just think of it as one loop between U and V. So you can think of it that, okay, there is only one loop. So the budget does not change. You just deleted some edges from the graph. Okay. There is a rule 3. So what are the rules? Of course, okay. So you have to delete. So another rule, which is maybe rule 0, or maybe that is not good. So isolated vertices cannot take part in forming any cycle. That is something we can stop worrying about. So if there is if you identify a vertex V, which is leaf vertex, so or if you identify a vertex V, which is an isolated vertex. So basically, if you have a vertex B whose degree is at most 1, then this vertex cannot take part in the formation of a cycle. For a vertex to take part in a cycle, if there is a vertex which is in a cycle, it must have degree 2 or more. Then you can simply forget about it. You can say that, okay, this is not going to take part. So I am going to delete this vertex. That is my deduction. So G minus V, G minus V. But budget will not change because you're not taking this vertex as part of your feedback vertex. The budget remains same. All right.
Yes, so this rule number 3 is slightly not clear. What if I remove the vertex number V? Then is still, so K here is that I'm looking for the FVS of the size less than or equals to the K. And since this V is never going to become the part of the FVS, uh, but why this V cannot become the part of the FVS? My question is this.
So if you want to delete a cycle, I mean, if you want to destroy a cycle, then you have to delete a vertex which is forming, which is a constituent vertex of the cycle. For example, look at
Yes,
the cycle. So this is a cycle. And if we want to destroy the cyclicity here, then a vertex which is part of this cycle should be deleted. Now,
right.
any vertex which is part of a cycle has minimum degree 2.
Mhm.
If there is a vertex which is outside of the cycle, degree 1, then deleting that vertex will not destroy cyclicity anywhere in the graph.
Yes.
So therefore, if you have a vertex whose degree is at most 1, then that vertex is irrelevant for the purpose of computing the FVS.
Yes.
This rule, that's why, is not changing the budget, because the budget will change only when you will make a decision about inclusion of a vertex into your FVS.
Right. And what about the reduction for the rule number 2? Is there any reduction in the problem formulation, or simply we can remove some of the multiple edges?
Yes. So let us say that there are 4 parallel edges you have identified, E1, E2, E3, and E4 between 2 vertices. Then the reduction is you remove all but 2 edges in this out of this parallel edges. So you can write that, okay, I am going to uh, reduce G2 G minus E1 minus E2, and the budget is unchanged. So you can say that we have G minus E1 comma E2 while the budget is unchanged.
Yes.
So you can delete all edges, parallel edges except two, so that you retain the information that there is a cycle here, which at some point you have to destroy.
Yes.
Okay. There's five rules. So another rule is that if you identify a degree two vertex, so what can you say about a degree two vertex, whether it will take part in a cycle or not? It is not immediately clear. So whether uh, degree two vertex, in this figure I'm showing a degree two vertex, whether it will take part in a cycle or not is not clear, but it depends on the rest of the graph. So it may happen that these two adjacent edges, these two neighbors, let us say that neighbors are n1 and n2, neighbor 1 and neighbor 2. So how this neighbor 1 and neighbor 2, if there is a path between neighbor 1 and neighbor 2, then uh, they will be part of a cycle, otherwise not. So in this case, what you do is that yeah.
Yes, so in this case, we can, I mean, like a recursion kind of the thing, like say, uh, so we can write a recursive equation kind of the thing by taking the help of the previous uh, three cases. Like say, there could be a self loop at the vertex v1, or there could be a self loop at the vertex v2, or it could be uh, the case RR3 as well. I don't know.
So you're saying that the other reduction rules that we have already defined can be reused somehow to define this reduction rule.
Yes, because the degree 2 case can be arised either if it is the case of the parallelizes, or it is the case in this figure which we have drawn here, that a single vertex and having two edges. So now if a single vertex is having two edges, so now basically we are, I mean, divide and conquer kind of the thing we may use here, I think, wherein so there would be a reduction of the number of the vertices, and yes, so there would be a reduction in the value of k also. That is quite possible if we can
That is
formulate.
yes,
Yeah.
yes. So if you can guarantee that now I am now confident that one vertex is identified, which will go into the FPS, which will be part of the FPS. Then only we will reduce the parameter from k to k minus one. So in this case, you are looking at a vertex. This vertex has degree two, and beyond that, you don't have much information. So you're not really sure whether this vertex, deleting this vertex, is going to be helpful as far as destroying cycles are concerned. So you're not really sure. The confidence is not yet there. So in this case, what you are suggesting is maybe we can do look back and see what we can do. Uh, so maybe there are ways to sort of formulate reduction rules using what you said. But what is done in the lecture is they don't worry about fee and they delete fee because we don't really know whether these uh, going to be part of my FBS, and we don't update uh, the parameter. So you understand what we're doing. So deleting key because we don't really know whether it is going to be part of a cycle or not. And since we're not confident, we're not updating the parameter k. Uh, does it look convincing?
Yes, yes, it is convincing. Because whatever I said is included in this fact that if I remove v from here, if it is contributing to a cycle, then also V is of no use. And if it is not contributing to the cycle, then also, yeah, we can always reduce it. Yeah, so in both the cases, yes.
But there is a problem. So this is not the full description of the reduction. So as soon as you delete V, what happens is you lose the edges which are incident to V. So even if there was a cycle, so let us say there was this other path between N1 and N2, then you wouldn't in the future think that there was a cycle here, because you have, as soon as you have deleted V, the fact that there was a cycle containing V is lost. So if you want to retain that fact, if you want to retain that information that there was indeed a cycle in this graph where V was a constituent vertex, then what you should do? Along with deleting V, you should do something. We should make a construction.
Yes, yes. So there could be a possibility that via N1 and N2, and including the vertex V, there could be a cycle.
Correct, correct, correct.
So,
So deleting V blindly is not the wisest of things.
mhm, yes.
A
So we'll
construction
have to
needs to be
look.
done. Yeah, I give it a thought.
Yeah, so
So you want to retain this information. Even after deleting V, you want to retain this information that there could have been a cycle that involved V. If there were no cycles, then fine. So you want to make a construction that retains the originality of the graph.
yes. So then I can think of a case. Say if we can somehow show that there is either a direct or the indirect age in between N1 and N2. So then I can show that yes, definitely there would be a cycle through the vertex V.
Yes, 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 yes. That is exactly what they do. That okay, you delete V, but to retain that information that there could have been a cycle involving V, you do this and add an edge between N1 and N2. So now you can see that the original property of the graph with respect to cycles is retained. Because if there was a cycle before, there is still a cycle now. If there were no cycle before, there are no cycles now. Fine. Shall we move to the next rule? Okay, so the next rule is if at some point your k is reduced below 0 and you still don't have an empty graph, then you output that there is no uh, feedback vertex set of size at most k.
So there is a small request. If you can please read the chat and can we meet at 7? Can we take the break you indicated now and then
So
we can?
we'll meet at 7. Thank you.
Thank you so very much.
Welcome back. Am I audible?
Yes, audible.
Okay. So we were discussing this question that in this randomized algorithm that we have seen in this week for computing a feedback vertex set, uh, which of these two facts are true? I mean, which of these two statements are true? One of these is a fact, the other one is a fallacy. So So some algorithm has to be run. So we were discussing that what is that randomized algorithm which we have seen in this week that can compute feedback vertex set. So first thing was that we have this graph, and the question is whether there exists a feedback vertex set of size at most k, and we reduce it to a smaller graph. So certain vertices are deleted, certain edges are deleted, and there are so many rules to do this reduction. So I think the last rule I was discussing is that if at some point the parameter gets reduced below zero, that means the budget is exhausted and the graph is still not empty. That means there is no hope for us to delete at most k vertices uh, to remove all the cycles. All right. So this is the reason we will say no, there does not exist feedback vertex set of size at most k. So these are the five reduction rules. Any doubts on the reduction rules?
No, these are clear. Uh,
Okay.
except in the notation of say RR1 and RR3, I think that both the notations are same, G minus V and as well as G minus V here, and there is no other difference. Except the difference of the notation, no other difference.
You mean these two?
The reduction wrote for the rule number one, RR1. This is G minus V. So is the minus the same thing or something else? I mean,
There's a G minus V only. Oh, you mean so you mean why there's a straight line and there is a slanted line? That's
yes,
what.
yes, yes,
No, no,
yes.
just the same thing.
Okay,
So
okay,
we
yeah,
want to say that a vertex as well as the incident edges to that vertex are deleted from the graph.
yes, yes.
All right. All right. So now, what is the algorithm? So now you have this graph, and on this graph, we want to do something by tossing coins. So whenever we have a randomized algorithm, we will make decisions that will depend on the outcome of a coin toss. Okay. So what happens is that on this graph, there are so many edges. So I'm going to draw this graph somewhere, G dash K dash. Maybe I'll just go above. Yeah, so I guess this thing should be pushed down so that we can see everything on the same page. So we know the rules. We don't worry about the rules. We'll see what is the algorithm, a randomized algorithm. That's what it's not possible. Anyway, so now we're looking at this graph. So I am constructing this graph, and by virtue of the fact that we have applied all the reduction rules, there does not exist any vertices of degree 0 or 1 or 2. So all the vertices have degree 3 or more. That is the nature of the graph we have got after applying the reduction rules. So this is a possible G dash. There, I think there are all degree 3 or more vertices in this graph. Yes. So now what you do on G dash, you pick an edge uniformly at random. So that is the step. So pick an edge uniformly at random. So it is generally abbreviated as UAR. That is, if there are k edges, then the probability of picking any edge is 1 by k. So the probabilities are uniform. All right. And
Yes, there is a
yeah,
vertex of the degree 2 as well in this diagram.
all right, all right. Now this is okay.
It's okay now. Yeah.
All right. So what you do is you have this G dash, and in G dash you pick a vertex uniformly at random. So and what does uniformly at random mean? That okay, there are so many options you have. You have, let us say, k edges in this graph. You could have chosen any of these k edges. So for every edge, uh, uh, so so the thing is, what generally people do is, so they generate a random number between 0 and 1. So they partition the interval 0 and 1 into k parts. So this is part one, P1, part 2, and part 3, and so on. There are k parts. So then they generate a random number between 0 and 1, and depending on which part that random number falls, they choose an edge. So that is generally what they do. So they have to ensure that every edge is picked uniformly at random. Okay. And now, uh, suppose I have picked this edge. So I did this experiment, and it turned out that this edge was picked. Now, one of the endpoints uh, of this edge is picked into the feedback vertex set. Let us say S be the FVS, feedback vertex set. Then what I do is I will pick one of the, let us say this is UV. So again, I'll toss a coin, and with 50% probability, I'll pick U into S, and with 50% probability, I'll pick V into S. So let us say U goes to S. And then I repeat the experiment as long as, say, whenever I have picked U, then so many cycles got deleted. So if I pick U, for example, then all these edges which are incident to U will get deleted. So I will get rid of many cycles already. And then I will repeat the experiment. And whenever I see that all the cycles are deleted, I will return that as a feedback vertex set. So that is the description of the algorithm. So are there any questions on the description of the algorithm?
Yes, so this thing is not clear. Can you repeat this explanation of the algorithm, that what happens when I remove the edge U and V? So we only consider those edges which are incident on U and not those edges which are incident on V, vice versa? Uh, is my voice clear? I
Yeah,
cannot hear you.
yeah. So I'm saying that uh, first step was to identify an edge UV, and the next step was to pick one of the endpoints into your feedback vertex set. So now, with 50% probability, with zero point 0.5 probability, you could have taken U, and with zero point 0.5 probability, you could have taken V. Now, if U is taken into the feedback vertex set, then all the edges incident to U uh, are getting deleted because uh, the ability of U to destroy cycles is only limited to those cycles where these edges, which are incident to U, are taking part. So that is why those edges which are incident to U are deleted. Now, if there is an edge which is incident to V, then I do not know whether this edge is taking part in a cycle or not. So if I take, I can, so if you had a different algorithm, if you had taken U and V both into the FBS, then you could have deleted the edges which are incident to V as well. But this algorithm, we are picking one of the endpoints of UV, and whichever endpoint you pick, you delete the edges which are incident to you, to that vertex.
Yes, yes, it's clear.
So now the fact is, so if, let's look at this figure once again. So if you had taken, so so see that in this G dash, there are only large degree vertices. So you already got rid of degree 2 or less vertices, you already got rid of them. So all the vertices are degree 3 or more. So intuitively you can think that the vertex which has more degree is more likely to be uh, taking part in many cycles.
Yes.
So, but we are doing a randomized experiment. That's why we're not being greedy and saying that, okay, pick that vertex which has more degree. Because our analysis with a greedy rule can become very messy. With this simple rule that, okay, with 50% chance, with 0.5 chance, I will take U, and with 0.5 probability, I'll take B. The analysis becomes simpler. So maybe we will get a with some probability we may not find an sorry feedback vertex set even if it were there, but the analysis becomes simpler. So that is why they are doing this. So now what happens is at yeah
But yes, so even though we are using randomized algorithm, but then the vertex which has got the highest degree, a higher degree, is likely to be selected with a higher probability. Even though we use UAR, wherein all the vertices or all the edges are likely to be selected at random. But clearly, the vertex which has got the highest degree is, I mean, it would be having higher chances of getting selected every time.
you mean that an edge which is okay, so you're saying that if we are taking UV, then it is uh, because let me put it this way. So we are picking an edge uniformly at random, but if there is a vertex which has a very large degree, then many edges are incident to it. Then the probability that we'll pick an edge which is incident to it also increases.
Uh, yes, I mean to say this only, but probably this won't be the case because once we select an age at random, then I can forget about the remaining ages, and I've got an age having two endpoints only. So then the probability of selecting every endpoint is same, that is zero point 0.5. Yes, this is true, and the
Yes,
degree
yes,
part
yes.
was, yeah.
Degree part will help. What you said is indirectly true because suppose there is a very high degree vertex in the graph. So let us say I'm being very concrete. Let us say there are overall 100 edges. All right. So then the sum of degrees is only 200. And let us say there was in fact a vertex which had degree 50. So it contributed 50 to the sum of degrees. Then there are 50 edges incident to it. So out of the 100, we are picking an edge uniformly at random. So there is a zero point 0.5 chance that we will pick an edge which is incident to this high degree vertex because 50 edges are incident to it, whereas overall there are 100 edges.
Yes.
So indirectly you are correct, but that is not the description of the algorithm. Description says that pick an edge uniformly at random, and then you pick. Let us say we'll say that this edge is called E. Then you pick an endpoint of E again uniformly at random, or we'll say it this way that second step is pick U or V into. I mean E is UV, so pick E or V into S again uniformly at random. That means with equal probability, 0.5, 0.5. Okay, so then you proceed, you keep doing that as long as you don't have an FBS or you have an empty graph. Uh, Fine. So what has happened? Okay, now the question is, uh, now we can read the question. So we use pre-processing rule so that in case of a yes instance, that if you have been given a graph for which there in fact indeed exists a k or smaller sized FBS, then the fraction of edges going out of G minus S. So S is the FBS compared to the edges with both endpoints in G minus S is at least half. So let us identify a feedback vertex set in this figure. Okay, so then we will be able to understand what has happened. So let us say we pick this guy and this. So once we pick this, all these edges are lost. Then we can pick this. This edges will get lost. Then we can pick this. This edges will get lost. I think these three vertices are sufficient. So let's try to do that. So this this these two is a feedback vertex of no. This cycle will still remaining. So can we say that these three red vertices, if we delete them, then all the cycles will get deleted?
Yes, yes. Yeah.
Correct. So this cycle, which is the outer boundary, to delete this cycle, I am picking this vertex. Now, even after all these edges have gone, uh, oh, this is not necessary to pick this anymore. So this is not necessary. No? No. This is necessary because even after I pick this guy, this triangle is still remaining, and this triangle is also remaining. So anyway, so let's say that this red vertices together, they form S. Now they're saying that the fraction of edges going out of G minus S. So G minus S is remaining vertices. So all the blue vertices are G minus S. So this guy, this let's take blue. So this 1, 2, 3, 4, 5 vertices are in G minus S. So now the statement is the fraction of vertices which are going out of them. So how many the fraction of edges going out of G minuses compared to the edges with both endpoints in G minuses. For first, how many edges are there with both endpoints in G minuses? So G minuses is this thing. So 1, 2, 3, 4 edges are within G minuses. Okay. So this guy, this guy, this guy, this guy.
Yes.
Now how many are going out of G minuses? So this is G minuses. Out of G minuses. So 1, 2, 3, 4, 5, 6, 7. So there are 7 edges which are going out of G minuses, and 4 edges are within G minuses among the vertices of G minuses. So that's what they're saying, that there are more edges. The fraction of edges going out of G minuses is more. Okay. So that is what the statement is. Okay. And now, so there is a lemma. So I will write down the lemma. So we have verified that this is true, but let us also look at the formal lemma. So the lemma says the following. This is a key lemma. So it says that let G be a graph of minimum degree 3, like in our case. So we have applied the reduction rules. So that minimum degree has become 3, at least 3. And let S, which is a subset of the vertex set, be an FBS. feedback vertex set of G. Then the lemma says that more than half of the edges of G are incident on X. Did I say X? I mean to say S. So what does it mean? So it means that most edges are sort of incident on S, so sort of going out. Uh, what does it mean? Incident on S. More than half of the edges of G are incident on S. Uh, what does it mean? So something which is incident on S must have come outside of S. So they should be going out of G minus S. So these two things are equivalent. Okay. So let us look at the statement once again. Although in this figure we are convinced. So what does it say? It says that the fraction of edges going out of G minus S. That means which are going out of G minus S means they're going into S, incident on S, compared to the edges with both endpoint and G minus S is large. So that's what it is saying. So now you understand the algorithm. And the crucial fact is that because of the reduction, G dash K dash is now only containing degree 3 or more vertices. That is why we are able to say this. Otherwise, we wouldn't have been.
So, yeah, so where is the use of the randomization here really? Because we could have we could have developed a heuristic like start eliminating the vertices in the decreasing order of their degrees and till no more cycle remains in the graph. So then also we could have, I mean, solve this problem. So how randomization really is contributing in the development of the solution then?
So you're saying why we didn't go by the greedy principle.
Yes, yes,
So you're saying that just do the pre-processing. That means get G dash from G by apply the reduction rules, and then apply the greedy principle.
yes, yes. I mean, we have listed five rules here.
Yes.
So we could have used them, and so I don't know how randomization is fruitful here. Uh,
So the thing is, whether or not we will get a feedback vertex set uh, uh, by applying the greedy rule is not clear, because since it's a NP complete problem, so it is not possible to find a polynomial time algorithm, and the greedy algorithm runs in polynomial time. So there is a good chance that for many instances, the greedy algorithm will give a very bad uh, uh, solution. That means so even if there is a k-sized FES, the greedy algorithm will fail to find it because of the inherent hardness of the problem, which is known because of its NP completeness. Now, what randomization? So randomization, what it so if you look at the entire video, so this algorithm is. So I think the next question it will become clear. Just a second. Uh, no, not in the next. So in this question only, I will tell you that the probability with which we'll find a k-sized uh, uh, feedback vertex set will be will be a substantial number. Okay, and then if we so let us say with some probability p we will find the feedback vertex set if it exists, And with 1 minus p, we will fail to find it using this algorithm. It can be analyzed. So that number p they have calculated. So I'll write it down. So p is the probability of your success. What is success? That you indeed recover a feedback vertex set of desired size. Then 1 minus p is your probability of failure. Now, if you repeat this algorithm many times, then your probability of failure will become, let us say you repeat, I don't know, let us say you repeat m times. So m iterations, you run this algorithm. Then your probability of failure will be only 1 minus p to the power m. Okay, now think of p as a concrete number. Let us say p is 10%. Okay, so 10% is the probability of success. Then the probability of failure is 90%. So 1 minus p is 0.9. Now what happens to 0.9 to the power 100? Suppose you run it 100 times. So 0.9 to the power 100 is a minuscule number. So your probability of failure has become tiny, very tiny. So you can be highly confident that if I run it 100 times, a large number of times, then I will succeed at least one time. So that is why randomization helps. That okay, I know for a fact that this is not solvable in polynomial time, but with good chance I will find it in reasonable amount of time in FPT time. Do you understand?
Yes, yes.
So always whenever randomization will come, think of it as a coin toss. Suppose your coin is biased. Your coin is biased, and 10% of the times only it comes heads, but 90% of the times it comes tails. So you know that if you are choosing heads, then your chance of your probability of success is only zero point 0.1. But if it is repeated so many times, then you will see at least one head in 100 coin tosses will be quite high. So that is the point. That with repetition, this is called boosting, the boosting of the probability of success. The success probability can be boosted with iteration.
Yes.
So this is true that most of the edges will sort of go out of G minus S. And the other thing is the fraction of edges going out of G minus S compared to the edges with both endpoints and G minus S is small. That is false. So one statement is the complement of the other. So
Yes.
let's go back. Now we can look at second question. So I think we are going slow, but since it is not necessary to cover everything, it is more important to clear doubts. I think that is fine.
Yes.
So let us look at the second question.
So, which of the following statements are correct? Number one, the longest path problem is known to be polynomial time solvable. So that is not correct. The shortest path is solvable in the polynomial time, but the longest path problem and as well as the long path problem, uh, I don't know
Yes.
how the long and the longest path problem both are related, but both are considered to be NP complete. So, and even I would be interested in knowing that why the longest path problem is NP complete. Because do we take the loops or the loop kind of the thing into the consideration so that every time I traverse a loop, I would be getting a path longer than the previous one, maybe because of that, or what is the reason of making this problem interactive?
All right. All right. So first thing is whenever you claim that a problem is NP hard, then you have to give a proof of that in terms of what is called a reduction. So let us see that with this question because you asked. So let's copy these four options, and then we'll see. Just copy. My iPad has become very slow.
Yes,
Okay,
and with your hint, I can remember one more thing, that probably the Hamiltonian circuitry problem can be reduced to this longest path, but I don't exactly understand that how those two problems are related.
all right, all right, all right. So first thing is there is a. So when you say that something is hard, and then you say that okay, I know this is hard because this is equivalent to this other problem, which is known to be hard. So you start with some source problem, and you show that your problem at hand is equivalent to that source problem, and you know that it is already known that the source problem is hard. Okay. uh, so showing the equivalence between a known hard problem and a problem at hand is called a reduction. So now, as you said that okay, maybe this problem called the longest path problem is equivalent to the Hamiltonian cycle problem or the Hamiltonian path problem, because we should compare apples to apples. So let us say we will reduce the Hamiltonian path to longest path. So then somebody might ask that where does the Hamiltonian, I mean, where from the Hamiltonian problem is reduced? So what is the equivalent of Hamiltonian problem? So at some point you will reach a dead end that okay. So now you have to prove something. So the first point, the first problem which is hard could not have been proved by comparing it with something which was known to be hard, right? So there is a source problem which is the mother of all source problems, which is called the satisfiability problem. So that problem was not proved to be hard by reducing it from something else. Every other problem is proved to be hard by reducing it to something else. I mean, uh, did I say the right thing? Sorry. Uh, I mean to say the following. I will repeat. Maybe I said the wrong thing. So, so you have a hard problem and you reduce it to the problem at hand. Then the equivalence is established. So there is a hard problem and you reduce. So we call it a polynomial time reduction. So we'll say that P1 is a problem. This is a symbol. It's polynomial time reduced to P2. So the reduction is from something which is known to be hard, and it reduces to a new problem, and then we say that the new problem is as hard as the known problem at a high level.
Yes. Problem P2 is at least as hard as the problem P1 is.
But then you understand that okay, so P1 is making P2 hard, then somebody must have P1 must have made P1 hard. So which problem was reduced to P1 and so on? You can trace a path, but at some point you have to end. So that problem is a satisfiability problem. And for that problem, a non-reduction based argument is required. So something that has to do with Turing machines, saying that there is something called the halting problem. And then the halting problem is not solvable in polynomial time. And because it's a fundamental computation issue, so that's why we say that, okay, now the satisfiability problem is hard. Now you can say that from satisfiability, show which all problems are hard. So somehow with some reduction, it was shown that the problem of finding the Hamiltonian path in a graph is NP complete. So what is the Hamiltonian path problem? In this problem, you are given a graph. Okay, so the graph is, let us say, on n vertices and m edges. All right, so number of vertices is n, and number of edges is n. So you have to give a path from starting from a vertex. You have to give a path that uh, touches every edge and does not intersect itself. Okay. So what I'm saying is the following. So you have a graph. You start from a vertex and you are drawing a path. You are tracing out a path. You don't want to reuse a vertex. And then you want to touch every vertex. Okay. So can you compute such a path? That is the question. Because self-intersection is not allowed. You cannot reuse a vertex. So you cannot say that, okay, I am going from V1 to V2, then V3, then V4, then I'm going back to there. This kind of things are not. This is a walk. This is what is called a walk, where repetition is allowed. Where self-intersection is allowed, that is called a walk. Whereas in a path, you do not want repetition. Is that fine?
Yes.
Okay. So now, what is the longest path problem? So what is the long path problem? So the long path problem is saying that, okay, can you give me a path uh, uh, which is as long as k? So can you give me a simple path which is non-self-intersecting, which is a sequence of k vertices where none of the vertices are repeated? That is a long path problem. So does there exist a k long path? So along with the graph, you're given the parameter k. K is given. The question is, can you give me a k long simple path, non-intersecting, non-self-intersecting? So now you understand that if k is set to n, that I want you to give a path that uses all the vertices. So it's a sequence of all the n vertices. Then you come back to the Hamiltonian path problem. So the Hamiltonian path problem is a specialization of the long path problem. So the specialization is by setting the value of k to n. So that's, if somebody can solve the longest path problem by simply invoking the same algorithm for the longest path problem, they should be able to solve the Hamiltonian path problem, but that is known to be NP complete. So therefore, such an algorithm cannot exist if you believe P is not equal to NP. Does it make sense?
Yes.
All right. So we will say that this first statement, that the longest path problem is known to be polynomial times solvable, is false, and NP completeness is true.
So how this long path is related to the longest path? Since we cannot solve the long path, so therefore getting the solution of the longest path does not arise. Is this the only reason, or is there any other reason as well?
It depends on the definition. Let me check what how they have defined. So let me look at the textbook and see in this context how they have defined. Just give me a moment.
Okay.
I will open the book. Longest path. So you are attending the complexity theory course.
Yes, yes. So there in that course, in one of the problem solving session, the long path and the longest path problem was discussed, but somehow that doubt remains unresolved. Actually, the difference in between the long path and the longest. What I could understand was that since we cannot solve the long path, so therefore getting the solution of the longest path does not arise.
So I'm looking at the book and exactly what I said. This is what is written. So the definition of longest path problem is the following. As an input, you are given a graph G and an integer K. And the question is, does there exist a path in G consisting of K vertices? So when they say path, it is a simple path. So does there exist a path in G consisting of K vertices? That is the longest path problem question. But let me see if they have defined long path separately. So I do not see a definition of long path. So as far as this question is concerned, longest path means that you are given this graph GK, and does there exist a path of length K?
Uh, okay. So then the second is true. First option is false, and the second one is true.
Yes, yes, yes. That is right.
Yes. Yes.
So let's look at the second question. So in the tree sub-isomorphism problem, tree subgraph isomorphism problem, we are given an undirected graph G and a tree T on K vertices. And the objective is to decide whether there exists a subgraph in G that is isomorphic to T. So what is isomorphism is known to you?
Yes, yes. So if we can find a mapping which is one to one and onto kind of the mapping, then there exists an isomorphism.
Correct, correct, correct. So if you can get a copy, so if you say that, okay, two graphs are given, but these two are in fact copies of each other, subject to some one-to-one mapping of the vertices in terms of the edges, then that those two graphs will be called isomorphic. And in this question, they're asking that, okay, you are given a tree on K vertices and an undirected graph G. So can you tell that whether there is a subgraph in G which is isomorphic to T? So remember that the isomorphism question, that whether given two graphs G1 and G2, they're isomorphic, that question is NP complete. One cannot decide.
Uh, yes, yes. Graph isomorphism is NP complete. Is NP complete or yeah, I don't remember exactly, but people consider this graph isomorphism problem as something very special because of certain reasons, and I don't remember those exact reasons. Probably this
Okay.
graph isomorphism is a problem which is there in NP as well as in co-NP or what. Something is special with the graph
Uh,
isomorphism problem and which is not there with the other NP class problems.
yes, 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 yes. There could be some additional properties which you are pointing to. That could be possible,
Yes.
yes. So I don't know about these properties. I think someone who has expertise in complexity theory can tell. Uh, uh, but yeah, so uh, our concern here is to decide whether this question is polynomial time solvable. And can you use the longest path problem to say something about this? So
Okay.
tree can be thought of as a path. So a path is also a tree. So now you can think about it.
Yes. So if I take a what is that? If I take a subgraph of the G, and if I try to map one to one, if I look for one to one mapping of the vertices, so then at one point of the time, I would be mapping a vertex. So the longest path problem will come into the picture in the sense that I'll have to find that can I make a move? I mean, so the leaves must map to the leaves. So that kind of a thing. So somewhere I'll have to find that does there exist a path from a vertex to the other vertex of the specified length. And that path should be the longest one in the sense that a leaf of the subgraph of the G is going to map to the leaf of the given tree T kind of thing. Uh,
Yeah, that could be one of the ways to look at it. Uh, I'll put it this way. So let us say, for the sake of contradiction, then that there was a known polynomial time algorithm for the tree subgraph isomorphism problem. There was an algorithm. Let us say we call it ALG. So let us say there is an algorithm. There exists an algorithm. We'll call it ALG capital that can solve this tree subgraph isomorphism problem in polynomial time. So we suppose that this is the case. Okay, so then we want to say that, okay, if this is the case, can we use this algorithm to somehow solve the longest path problem in polynomial time? If I can do so, then that is a contradiction.
yes, yes. So yeah. So like say so we would be mapping basically the vertices which are one edge away from the root in the subgraph of the G to the one edge away from the root in the tree, and similarly the vertices which are two edges away to the two edges away. So in that sense, if that could be the interpretation of the isomorphism, then I can apply BFS kind of a thing over both the subgraphs. I mean, both the subgraph of the G and the tree T, and keep on mapping the vertices. And will that mapping be one to one and onto kind of the mapping? So yes, that can be done in the onto type of the mapping. Then I can solve it in the polynomial time, I guess. And how is this related to the longest path problem then? Probably my previous argument was not that correct.
Okay, so let us say that uh, this algorithm exists and we want to use this algorithm to solve the longest path problem. So first of all, uh, we have this graph, and what is the meaning of finding a longest path? The meaning of finding a longest path is just finding a k path. That means a path which is a sequence of k vertices. Okay. So if I suppose that the tree on k vertices is a path instead of a tree. So let me draw it somewhere. So I will push these things downward. Uh, okay, so this gonna go down. Oops. Yeah, fine. So there's enough space now. So suppose that. So what is your input to this question? So there's a graph and there is a tree. And you are the question that you are asking is, do you find, is it possible for you to give me a subgraph of G which is isomorphic to T? So first is I want to visualize, I want to imagine this tree as a path. So instead of a tree, I take a path. So this is a K path. Let us say there are K vertices. Okay. And so what do I know? I know that there is an algorithm by my assumption that can solve this tree subgraph isomorphism problem in polynomial time. So that means this algorithm can tell me whether there is an isomorphic copy of this path in my graph. And if it exists, then that means there is a long path of length k in my graph, isn't it?
This is not clear. Can you repeat this explanation, please?
Okay. So what is the tree subgraph isomorphism problem? You are given an undirected graph G and a tree on k vertices. So G comma T. And the objective is to decide whether there exists a subgraph in G that is isomorphic to T. Okay. Now I assumed that the T is nothing but a path on k vertices.
Okay.
And I also assumed that there is, in fact, an algorithm ALG that can tell me, irrespective of what T is, whether there is an isomorphic copy of T in my graph as a subgraph.
Mhm.
So now, if I apply this algorithm ALG on the given graph and this path as T, then depending on whether this algorithm says yes or no, can I answer the uh, longest path problem in this graph G?
So now that is the question, that how this subgraph of G, how the vertices of the subgraph of G are going to map to this instance of the tree T, based on the degree of the vertices, like say, so so since here we have only two vertices of the degree 1 and remaining vertices of the degree 2, so therefore we would be mapping the degree 1 instances to the degree 1, and getting the first vertex of the degree 1 would be easy, and getting the last vertex of the degree 1 would indirectly be the solution of the longest path problem, or what?
So I think in your mind the definition of subgraph is blurry. I think you are confusing subgraph with induced subgraph. So when I'm saying that there is a isomorphic copy of this path in my graph, I'm not saying that exactly such a thing is there. I can allow other vertices to be connected to this path. So this is a probable graph G in which this piece of uh, this path exists as a subgraph.
Okay, okay.
So what you are thinking about is induced subgraph. Induced subgraph means when you take a let's first look at induced and so I think this I discussed some time ago as well. So if I give you, so let's say this graph, this is my graph, let us say, and let's say I say this vertices are 1, 2, 3, and 4. So this piece 2, 3, 4 is in fact a subgraph of my graph G, but it is not an induced subgraph because there is also an edge between 3 and 4 which I am not taking. So when you say that okay, I am giving you a subset of the vertices, give me the induced subgraph, then you have to take all the edges among the given vertices. But if you don't do so, then you still get a subgraph, but that is not an induced subgraph.
Yes. Yes.
So what has happened here is that I am asking that okay, if you have access to an algorithm which is able to solve the tree subgraph isomorphism problem in polynomial time, and also you assume that the tree is in fact a k-length path, then applying this algorithm on the graph, you will be able to retrieve a k-length path.
Yes.
But that should not happen because the longest path, k-length path problem itself is NP complete, we have seen before.
Yes. So my argument was this only, that if I consider say two specific cases, two specific instances, like in this instance, we have two vertices of the degree 1 only, vertex number 1
Yes,
and the vertex number k. So if I go for one-to-one mapping of the subgraph of the G, then getting the first vertex whose degree is 1 would be pretty easy. And we can consider that vertex as the root of the subgraph. And getting the other vertex of the degree 1, so we'll have to reach till the last vertex, and whose length would be k. So
yes,
yes.
yes.
Yes. So yeah,
There is
there is a relation. There is a relation between this algorithm and the longest path problem. Yes, there is.
all right, all right. So you were probably thinking it from a more elementary set of uh, steps. So yeah. So you did not reduce it directly. Instead of reducing it directly, you used some more elementary machinery so that you can get to the conclusion. But I think yeah, that is also another way of looking at it. Uh, Anyhow, so this lets us conclude that this problem is not polynomial time solvable. This will be false, whereas other statement that this problem is NP complete is true.
Yes. Yes.
So I have 2 minutes, and I will not stretch it beyond that. So let's look at the question for a moment. Just I'll let you read this question, and I will tell you the answer. So maybe this is too specific to the video. Uh, Okay, so I'll tell you what the context is. The context is that in this problem, they're solving the longest path problem uh, using something called colorful paths, and then uh, uh, probability is coming because it's some randomized decisions are being made in the algorithm, and then they say that with high probability they are able to find the longest path in so much so time. And what is that probability? That is the first question. Uh, so I think this will require another half an hour of discussion. So I'll not go into the details of it, but the spirit of the algorithm is same as the algorithm that we have seen for the feedback vertex cover. That some coin tosses are being done, and decisions are made based on the outcome of the coin tosses. And then you have to calculate certain probabilities of success, and whether when and not when you will succeed and will you will not succeed. So there are some diagrams, as you can see, that some coloring of the graph for in the longest path problem is given. So and then based on the coloring, certain decisions are made. So I think we'll not look beyond uh, uh, deeper into this. Uh, all right. So I think thanks a lot for showing up on a holiday on Rakhi Bandhan. So I wish you all the best again. Thank you.
Thank you so very much. And this session was so very interesting. Thank you so much.
All
Good night.
right. Thank you. Good night. Yes.